Thank you very much for joining us today for the NTT R&D Forum Technical Seminar. My name is Shiba. I was just introduced a moment ago. I work at the NTT Science and Core Technology Laboratory Group, where I oversee the planning and promotion of research and development in advanced technology fields. The theme we will be exploring in this session is Illuminating the Future with Photonic Quantum Computing, from Fundamentals to Cutting-Edge Technologies. Each speaker will present for 20 minutes, followed by a panel discussion. We would now like to invite today's two speakers to the stage. Please come in. Our first presenter is Mr. Hiroshi Takase, Representative Director and Chief Executive Officer of OptQC. Mr. Takase has been featured in many media outlets, and I believe many of you already know him. He worked at Furusawa Laboratory, which was the first in the world to establish the basic principles of optical quantum computers. He later founded OptQC Incorporated in 2024 as a startup from the University of Tokyo. In the quantum field, where Google and IBM are competing, he is attracting attention in Japan and abroad as a leader opening a new wave of innovation from Japan. Our second presenter is Mr. Takeshi Umeki, Senior Distinguished Researcher at the NTT Device Technology Laboratories. Mr. Umeki specializes in nonlinear optical signal processing and quantum state control, and he is a leading figure in device research on the global stage. Now, we will begin with a presentation from Mr. Takase on the implementation of optical computing. Mr. Takase, go ahead.
Everyone, thank you again. I'm Takase from OptQC. Since today's theme spans from fundamentals to cutting-edge technologies, I will use these 20 minutes to explain the basics and lead into the advanced topics. To briefly introduce the company, as mentioned earlier, our roots are in the Furusawa Laboratory. Professor Furusawa, shown on the left side of the slide, invented the technique known as quantum teleportation, which became the foundation of optical quantum computing. His laboratory has continued since the year 2000, and many of its graduates now lead the management of this company. I also earned my doctorate there and served as an assistant professor, but I left the university and now devote myself entirely to OptQC. As for the social challenges that our company aims to address, we briefly spoke about them during the press conference last week. At the core, our goal is to create a new computing platform. If digital transformation continues to advance on today's computing infrastructure, there is a growing concern that, from an energy standpoint, the world will eventually reach a point where things cannot continue as they are. To address this looming issue, OptQC aims to achieve two major breakthroughs. The first is the quantum computer, which is also the title of today's talk. This means moving our computers from the classical domain to the quantum domain. It means altering the rules of information processing itself step by step and using quantum effects to reduce required computation steps. This is where algorithmic acceleration becomes possible. The second breakthrough is the shift from electricity to optics. This is closely related to what we call optoelectronic fusion. Today, when we hear the word computer, everyone naturally assumes that it runs on electricity. But 10 years from now, that may no longer be the case. I see tremendous potential in optical computers. By shifting from electrical systems to physical systems that operate with optics, we expect to see major advantages in processing speed and energy consumption. At the convergence of these two major trends is OptQC's objective, the optical quantum computer. From here, I will move into the technical content. First, before we get to the front line of technology, I would like to begin with the fundamental part. As a basic premise, let me briefly explain what a quantum computer is. If you search on Google, you will find many explanations, but in short, it's a new type of computer that uses something called a quantum bit to perform computation. The kind of computer we normally use is what we refer to as a classical computer. In a classical computer, information is expressed in bits. With combinations of zeros and ones, we represent many different kinds of information. In contrast, a quantum computer can use the freedom of superpositions of 0 and 1. As shown at the bottom of the slide, if we have 3 quantum bits, all 8 patterns from all zeros to all ones can be represented at once as a single superposition. A very naive way to think about this is that by computing all of these in parallel, the computation becomes faster. In reality, we use phenomena such as quantum interference to achieve algorithmic speedup, but as a starting point, it is important to understand this idea of superposition. Since these conceptual models of quantum computation were proposed, many different physical systems have been developed to realize quantum computers. This movement began around the year 2000, and there are many approaches other than optical systems like superconducting systems, which are systems using electrical circuits. Systems based on cooled atoms, where a single atom serves as a quantum bit, and though not shown here due to space, there are also ion traps, semiconductors, etc. After about 20 years of research, these approaches have produced test machines, as shown below, and actual quantum computers are now beginning to appear. This is the era we are currently in. Among the many possible approaches, I would now like to explain which method OptQC uses. This is something we have not stated very explicitly until now, but today I would like to say clearly that the OptQC method is an optical communication-based method. I hope to explain the many ways in which our approach is closely aligned with and compatible with optical communication. First, information embedding. I would like to explain where we embed information, which is into optical traveling waves. To put more simply, we embed information into light that is in flight. We do not encode information by using the presence or absence of a single photon, as in a discrete 0 and 1 particle-based encoding. Instead, we use the phase and amplitude, which are analog variables. We represent quantum information on the phase plane, which is very similar to optical communication. For example, on the left is an example of the quantum states 0 plus 1. This is a quantum superposition with equal probability of 0 and 1. If we try to imagine this physically as an optical pulse, it can be visualized as a superposition of an upward wave and a downward wave, light waves whose amplitudes are opposite. When we draw this on the IQ plane, it looks like a superposition of 2 coherent light states, as shown below. The picture on the right shows the amplitude distribution of a quantum bit that I measured experimentally, and you can see the 2 peaks clearly separated like 0 and 1. This is how we embed information in the phase plane. One advantage is that we can naturally handle analog information. Because we use the phase plane, both quantum analog information and quantum digital information, which is what we call a quantum bit, can be handled together. In the example on the left, the 2 separated peaks represent a discrete use of the phase plane, while the rest of the distribution is continuous, representing analog values expressed through superposition. This flexibility is one of the strengths of the approach. Furthermore, the phase plane is expected to have very high freedom. In this picture, we only see 2 discrete values, but in principle, we can create many more discrete levels. For example, if we use that freedom for quantum error correction, we can construct well-known codes such as the GKP quantum bit. The figure on the right shows such a state. It is created by superposing many different optical amplitudes. When drawn on the phase plane, it looks like the pattern at the lower right. It resembles a QAM 16 or 64. In classical systems, we embed many bits of information at once, but here, by treating them as superpositions, we use that freedom for quantum error correction. So we have seen that information encoding is similar to communication. Next, how do we perform operations on this information? We implement our quantum gates using quantum teleportation. Quantum teleportation circuits allow us to perform analog quantum processing on analog variables such as the phase plane. Although the gates themselves are analog, when we input a GKP quantum bit, as mentioned earlier, we can perform universal and error-correctable quantum computation even for 2-level quantum bit systems. I will not go into the detailed explanation of this circuit, but quantum teleportation is a protocol involving 3 quantum states. First, on the upper left, we have the sphere labeled input. Think of this as the input quantum state. This could be a GKP quantum bit or an analog input. The other 2 states shown below are the entangled pair. These 2 quantum states have correlated properties. By performing a special operation called the Bell measurement on the input and 1/2 of the entangled pair, the input state appears as the output on the remaining half of the entangled pair. Teleportation alone simply outputs the input unchanged, an identity transformation. However, by adjusting the settings of the Bell measurement, we can realize many different quantum operations. So this means we can not only transfer information, but also modify it and operate on it while transferring it. The simple diagram on the left illustrates this. With 1 input and 1 entangled state, we can perform quantum teleportation. However, teleportation alone gives us only 1 input and 1 step of quantum computation. I'm not sure if it should even be called quantum computation. To build a real quantum computer, we need something like n inputs and m steps, meaning we must handle a much larger quantum system. In that sense, we need a very large entangled state, like the one shown at the lower left, which can accept many inputs and also has enough depth to support multiple computation steps. A computational model that uses this kind of large entangled state is called measurement-based quantum computation. We sometimes call our approach a quantum teleportation-based quantum computer, or a measurement-induced quantum computer, and we describe it in various ways, but you can think of it as the structure shown in the lower left diagram. So we now understand that many kinds of computation are possible. The next question is how to implement this physically. How many teleporters do we need? For example, the single teleporter at the top can be implemented with the diagram I showed earlier. That seems simple enough. But if we need n inputs and m steps, that would suggest we need n times m teleporters. That quickly becomes a huge challenge, because even a single teleporter currently requires something about the size of a large laboratory table. If we try to support 10,000 inputs and 10,000 steps, we would need an enormous space filled with teleportation equipment. That's not realistic. Fortunately, there's a way to avoid this. The idea is simply to reuse a single teleporter. 1 input arrives, is processed, and is transferred to the output. Then, if we feed that output back as the next input, we can process many quantum bits over many steps with 1 teleporter. By using this kind of time-domain multiplexing, we can implement the architecture while preserving scalability. When we implement this idea of reusing teleporters, the system looks like this. Earlier I said we reuse 1 teleporter, but in practice, we need to perform 2-qubit gate operations. So the smallest unit actually requires 2 teleporters. This means we need 2 places to generate entanglement and 2 sets of Bell measurements. That combination becomes the smallest building block. This is what becomes the time-domain multiplexed processor. Up to the dotted line, we generate the large-scale entanglement shown on the right. It is a little hard to see, but at the bottom you can see many orange circles lined up. That is the input. Inputs arrive one after another in time with this system. If you focus on how this works, many quantum bits are transmitted along a single channel as a sequence of time-ordered data. This structure is very close in concept to optical communication. In other words, we multiplex information in the time domain and process it as it is transmitted. One advantage of this method is that the hardware size isn't affected by the number of increased inputs. Because we reuse 2 teleporters, the system size stays the same whether we have 1 input or 100. As you can see here, a 1-input system from 10 years ago and a 100-input system built recently are almost the same size. At RIKEN, we currently have a 100-input machine installed. As a gate-based optical quantum computer, this is the first system of its kind in the world. It is a system with 100 inputs, 100 megahertz operation, and cloud access. In terms of development, I also participated in making this, but the main work was done by Mr. Yonezawa, who works jointly with Riken, and Mr. Hiraoka, who at the time was at Fixed Stars Amplify. Here's an image of how this operates. A Python SDK called MQC3 has been released in a limited form, and you can use it to program the system. Anyone who writes programs will need at least a basic understanding of quantum computers. They'll imagine applying operations in sequence like the ones shown on the left. They describe all of these gates in MQC3 in the order they want them applied. When they run the program, a compiler on AWS sends it to the actual optical quantum computer at Riken, and the results are returned. The archived paper shows experimental results demonstrating this. Although this is not a quantum algorithm, it is an experiment that sorts input quantum states. On the far left, you see 5 optical inputs with different amplitudes. The circuit takes those 5 optical inputs and sorts them by amplitude. On the right, the same process is extended to about 100 inputs, and it successfully sorts them in ascending or descending order. That is the story at Riken. And now, although the company is only 1 year old, we are building our own first machine at OptQC. On the left is the traditional image of a quantum computer, with doctoral students gathered around a table adjusting everything manually. I call this a labor-intensive optical quantum computer. We want to move away from systems that require so much manual labor and instead modularize them to improve maintainability and stability. Our modular optical quantum computer will be unveiled next spring at AIST. And as mentioned in our joint press release with NTT, we aim to further miniaturize it into a rack-mounted form by around 2030, conforming to the 19-inch rack standard. After Machine 1, we plan to further merge with optical communication technologies. Recently, and Dr. Umeki will explain this in more detail later, the device known as the OPA has advanced significantly, and by using this, optical computers can achieve much higher speeds. In this experiment, we successfully measured an EPR state at 60 GHz. To give a sense of how remarkable this is, this technology could raise an optical quantum computer's clock frequency by more than 100 times. Because we use time-domain multiplexing, increased bandwidth means we can pack far more information into each unit of time. So if the clock becomes 100 times faster, the number of inputs and quantum states we can load also increases by 100 times. Therefore, using this technology, Machine 2, scheduled for completion around fiscal year 2027, aims to expand from 100 inputs to 100 times that, or 10,000 inputs. I will close by discussing an even further frontier, a place beyond Machine 2. If at the stage of Machine 2 we can perform high-speed measurements using OPAs and achieve clock frequencies of 10 GHz or even close to 100 GHz, the question becomes how to go beyond that. Now we have reached 60 GHz, but the OPA actually has a potential of more than 10 terahertz. So there's room for about 2 more orders of magnitude of improvement, meaning we are currently using only about 1% of the device's potential. We want to overcome this limitation. Ultimately, the bottleneck is the measurement device. The electrical circuits are limiting everything. Recently, equipment used for 5G communications, such as nearly 100 GHz measurement devices, has improved things somewhat, but the processing speed bottleneck is still on the electrical side. Therefore, when we think of the ultimate quantum computer, we believe it has to be an all-optical quantum computer. Most of the upstream part of a quantum computer is optical, but the downstream part is still electrical. We still rely on measurement devices and digital signal processors, and if we replace these with optical devices, in other words, if we replace the classical signal processing computer with a classical optical computer, then terahertz-class quantum computers become possible. Technologies such as silicon photonics or lithium niobate, which has recently become popular as TFLN, are technologies we are excited about, and we also look forward to the various devices emerging from the ION initiative and other optoelectronic fusion efforts. Besides this direction, we can also consider wavelength multiplexing, for example, by arranging many 100 GHz cores. But as one ultimate form, we want to pursue the realization of a fully optical quantum computer at OptQC. We are approaching 20 minutes, so I will end here. Thank you very much.
Thank you, Mr. Takase. First, I was a bit surprised to hear that the optical approach is an optical communication-based method. I believe you explained the conceptual aspects of optical quantum computers, its structure, and operating principles in considerable detail. And you showed us a concrete example of what's in use now with the machine at Riken and machines 1 and 2. And ultimately, the fully optical quantum computer. It was an inspiring and forward-looking presentation, and I believe many here found it exciting. Thank you, Mr. Takase. Please return to your seat. Next, we will hear from Mr. Umeki, who will present mainly on PPLN technology. Mr. Umeki, the floor is yours.
Thank you. I appreciate the introduction. My name is Umeki from the NTT Device Technology Laboratories. Thank you for giving me the opportunity to speak today. I will explain this in more detail later, but the PPLN device, which was introduced earlier as a parametric amplifier, functions as a converter between classical and quantum signal. I would like to speak today under the theme of advancing the fusion of optical quantum technology and optical communication technology through this device. As mentioned in Mr. Takase's talk, expectations for optical quantum computers rest on combining two leading technologies, cutting-edge quantum optics and the advanced optical communication technologies that NTT has been developing for many years. By merging these, we believe it is possible to build extremely high-performance optical quantum computers, and that is the basis for the strong expectations surrounding this field. As noted earlier, the announcement on the left refers to last year's launch at Riken of a new optical quantum computing platform, which incorporates the best of modern quantum optical technology. On the right is research I am involved in. Work on ultra-high-capacity communication has progressed significantly. And in August, we announced successful demonstration of very high-capacity, long-distance transmission using technology with a 27 terahertz bandwidth. These technologies are highly compatible, but they are not automatically interchangeable. To move between optical quantum signals and optical communication signals, we need a bridging device. And that role is played by the parametric amplifier. Today I will cover 3 topics related to this. To supplement Mr. Takase's talk, I will first discuss what an optical quantum computer is, then outline its similarities with digital coherent optical communication, and finally explain the optical parametric amplifier, which serves as a classical quantum converter. As mentioned earlier, optical quantum computers are expected to solve very complex problems that would take classical computers a long time, and many application fields are being considered. There are many possible physical qubit implementations for quantum computers. Including superconducting qubits and cooled neutral atoms. But one major advantage of optical systems is that they operate at room temperature and atmospheric pressure. Looking more closely at what distinguishes optical systems from superconducting, atomic, or ionic systems, the key difference is often described as standing wave versus traveling wave. These other systems require qubits to be physically placed in space, meaning they must be arranged and scaled spatially. In other words, they require spatial integration and parallelization. On the other hand, light is a traveling wave. At first glance, processing traveling waves appears difficult, but because optical signals arrive continuously, we can time multiplex them. Combining these techniques allows us to take advantage of properties unique to optical systems. Quantum computation is often explained in terms of the gate model. You place initialized qubits on the left, then apply gates along the circuit. A 2-qubit gate, for example, imposes a condition that the upper and lower qubits become entangled. As circuits scale up, generating entanglement at each required point becomes one of the most difficult aspects of gate operations. By contrast, in the measurement-induced model used in optical quantum computers, you first create a large entangled state, then progressively consume it during computation. Combined with time multiplexing, this allows extremely large-scale computation while keeping device size essentially constant. Another major point is that while we often hear about qubits in the context of discrete variables, optical qubits use continuous variables, which is a defining difference. By continuous variables, we mean what you see at the upper right, AM or FM modulation, where intensity, amplitude, and phase are combined through sophisticated modulation methods. This makes it possible to pack high-dimensional information into a single pulse. To summarize an optical quantum computer, we arrange the flying qubits along the time axis. We then encode them using continuous variables and carry out the computation by finally measuring them. In this way, we expect to realize a quantum computer that is extremely fast, fault-tolerant, and compact enough to be a practical device. Next, returning to the diagram on the far left, pulses of light are emitted from the optical source, travel forward, and are eventually detected. This setup is highly similar to optical communication, and I would like to use that similarity to supplement the explanation of optical quantum computers. To begin, I would like to give a simple explanation of what digital coherent communication is. Digital coherent communication consists of 3 major functional blocks. The blocks are the optical transmitter, the optical fiber transmission line, and finally, the optical receiver. The center part, the optical fiber transmission line, is entirely analog. The transmitter and receiver handle the digital modulation and demodulation of the signal. As shown on the left, we use 2 modulators to map the data signal onto the phase plane of the laser light. We then place data on the phase plane for each of the Y and X polarizations. In other words, transmitting 4 cosine and sine components. On the receiver side, there are likewise 4 quadrature amplitude detectors that extract those same 4 components. However, as light propagates through the fiber, wavelength dispersion and polarization mode dispersion cause waveform distortion. By the time the signal is received, it appears extremely noisy and almost unintelligible. Finally, digital signal processing performs adaptive control to compensate for waveform distortion, separate polarizations, synchronize phases, and demodulate the signal. This shows our latest results, which bring together the very best of these technologies and which we also recently announced publicly. By packing data densely on the phase plane, densely multiplexing wavelengths, and transmitting them across a very wide bandwidth, including the S-band, C-band, L-band, U-band, and the newly added X-band, we achieved long-distance transmission across 27 terahertz of ultra-wide bandwidth. When we compare digital coherent communication with optical quantum computing, in digital coherent communication, the amplitude of the cosine and sine components is represented as points on the complex plane. Optical quantum computers similarly represent their initial states as superpositions of squeezed light distributions on the phase amplitude plane. Furthermore, both systems use 4 sine and cosine components, with a transmitter, a transmission path, and a receiver. And on the receiver side, both systems perform 4 quadrature phase amplitude measurements and signal processing, making the technologies extremely similar. In this table summarizing these points, one difference is that optical communication uses coherent light and quadrature phase amplitude, while continuous variable optical quantum computers use squeezed light. There are strong similarities in signal generation and computational operations, but one difference is the need for squeezing operations, and another is the need to use non-Gaussian states, which I will mention later. To summarize the differences in this section, although optical communication systems and optical quantum computer systems are highly similar, there are 3 key areas where they differ. The first is whether or not the light pulses are temporarily entangled. The second difference concerns the signal points on the phase plane. In optical communication, each symbol point is independent. But in the case of quantum systems, even though the points look similar, they represent superposition states. The third difference is sensitivity to changes caused by optical loss. In digital coherent communication, even when there is optical loss, and even after optical amplification, although the signal-to-noise ratio does degrade, the fundamental state is maintained. In contrast, for superposition states and entangled states, once loss occurs, a conventional optical amplifier will alter the state when attempting to restore it. So this requires special care. To address this, we need high-quality squeezed light, the ability to generate non-Gaussian superposition states, and specialized optical amplifiers. To achieve these capabilities, I would like to introduce the optical parametric amplifier. Parametric amplification is very similar to amplifying the motion of a swing. When a person pumps a swing, they shift their center of gravity, which acts as the excitation. By matching the timing, the swing's motion grows larger. You can increase the motion or reduce it by shifting the timing. You can think of this as something like controlling a swing. To realize optical parametric amplification, we use periodically poled lithium niobate devices. The wafer shown at the upper left looks like transparent glass at first glance. But when light passes through it, it can generate various unusual states. To increase efficiency, we create periodic structures, use waveguide technology, and integrate the devices into modules that interface smoothly with optical fiber. To explain a bit more, we begin with the base crystal, then create a periodic domain inversion structure. Because the input light and converted light would otherwise develop a phase mismatch, aligning their phases enables high efficiency. By forming an optical waveguide to confine the light and allow long interaction lengths, we can achieve very high efficiency. The actual device fabrication process begins by creating the periodic domain inversion structure on the wafer. Next, the wafer is bonded to a support substrate of lithium tantalate. The LN core, which forms the optical path, is thinned. And then lateral processing defines the final waveguide. The finished chips are then mounted onto modules with fiber connections. Each module has two fibers, one for the signal and one for the pump light. We have been carrying out research and development for a very long time. Our research and development already started before the year 2000. In the early stages, we worked on developing highly durable lithium niobate wafers and establishing the basic techniques for direct bonding. From there, we introduced dry etching methods and high-precision photolithography technologies. Over the past 20 years, these efforts have enabled us to achieve roughly 50 decibel conversion efficiency and significant improvements in parametric amplification gain. The basic functions of PPLN are addition and subtraction of optical frequencies. Today's explanation focuses on the latter. One operating mode performs subtraction, and another is optical parametric amplification, where the original pump light amplifies the signal. Furthermore, by interfering the subtracted idler light with the amplified signal, one can create a special amplification mode known as phase-sensitive amplification. Briefly speaking, when pump light and signal light are input into the device, idler light is generated. This idler light is the converted output corresponding to the difference frequency operation. As shown in the figure at the bottom, this phase relationship is always opposite to that of the signal light. In other words, when the signal light rotates counterclockwise, the idler light rotates clockwise, so the output carries a phase relationship that represents subtraction. And when the efficiency is increased, both the signal light and the idler light are amplified. Normally, the signal and idler have different wavelengths and frequencies. But when they are made identical, a special operating mode appears. As shown in the lower left, when the signal and idler reinforce one another, amplification occurs. When their phases are orthogonal, attenuation occurs. This is phase-sensitive amplification, where amplification happens only at specific phase conditions, and attenuation occurs at the orthogonal phase. Phase-sensitive amplification offers two major advantages. First, it enables extremely low noise amplification. Second, by attenuating the orthogonal quadrature, it allows the generation of squeezed light, which compresses quantum noise. Here are the measurement results showing the squeezing levels achieved with our device. To reduce waveguide loss, we have tested multiple fabrication approaches. By using the low-loss blue-labeled dicing process shown on the left, we have succeeded in generating more than 8 decibels of squeezed light, producing a state compressed relative to the shot noise level. This squeezed light source is already implemented in our current optical quantum computer systems. It is also essential to generate non-Gaussian states. These are superposition states, with Schrödinger's cat being the most famous example. Non-Gaussian states are crucial resources for universal quantum computation and for constructing error-correctable quantum codes. Squeezed light is also needed here. In the wave description, we focused on quadratures, but in the particle description, we can understand why entanglement appears. When the pump photon energy satisfies the subtraction frequency condition, one photon effectively splits into two, creating an entangled pair. Because each event produces two photons, the output always consists of even photon number states. The graph on the right shows the photon number distribution for ordinary coherent light and for squeezed light. When the squeezing level is low, for example, the 3 decibel case shown in blue, the distribution is dominated by photon number pairs, that is, the 2-photon state. As the squeezing level increases, you can see that the existence probabilities of the 4-photon, 6-photon, 8-photon, 10-photon, and other even photon pairs becomes significantly larger. This even photon structure is what enables error-correcting codes based on parity. That is the fundamental idea behind such coding schemes. We have also succeeded in generating the most elementary form of a Schrödinger cat state. This state is created by subtracting a single photon from an even photon squeezed light stream, a mechanism well known in theory. We verified this experimentally in 2022. Since then, we have extended the method to subtract multiple photons, and we can now generate states corresponding to 1, 2, 3, and 4 photon subtraction. As mentioned earlier, achieving high speed is very important. The difficulty has been that quantum signals are extremely sensitive to loss, so detectors with exceptionally high quantum efficiency were required. Meanwhile, the ultra-fast detectors used in optical communications are indeed fast but have low quantum efficiency, meaning they could not be used directly. However, detecting the orthogonal quadrature is analogous to an electrical phase-sensitive amplifier. By replacing that stage with an optical phase-sensitive amplifier, we can obtain robustness against loss, enabling the use of high-speed detectors like those used in optical communications. We have already demonstrated squeezed light at around 43 gigahertz and measured EPR entanglement correlations at very high speeds of up to 60 gigahertz. Finally, to summarize, the optical parametric amplifier serves not only as a quantum light source, producing quantum light from classical light via squeezing, but also as a preamplifier for detection and as a converter that turns quantum light back into classical signals. It plays an extremely important role and will help drive the integration of optical quantum technologies with classical optical communication systems. That's all from me. Thank you.
Thank you very much, Mr. Umeki. Mr. Umeki, thank you for summarizing the similarities between optical communication and optical quantum computers, and for providing a detailed explanation of PPLN technology, which serves as both the heart and key device of optical quantum computers. Now that everything is ready, we would like to move on to the panel discussion. Mr. Takase and Mr. Umeki, please have a seat. We will now begin the panel discussion. Before starting the session, I would like to ask everyone a quick question. If you know about quantum, or know at least a little about quantum, could you please raise your hand? Ah, thank you. That's more than I expected. Richard Feynman, one of the proposers of the quantum computer, is said to have remarked that if you think you understand quantum mechanics, then you do not understand quantum mechanics. That is how difficult it is to truly grasp. My first question for you two, who are conducting research in such a challenging field, is this. What motivated you? What was the reason you decided to pursue research in this area? Let's start with Mr. Takase.
You mean the quantum industry, right, Mr. Shiba?
Yes, in terms of the quantum industry.
About 10 years ago, when I was a third-year undergraduate student, I was trying to decide which lab to join. I spent most of my time on club activities and was not a very serious student, but quantum computing was just starting to gain attention. This was before Google published its quantum supremacy paper in 2019, so the feeling was that the field was only going to grow from there. In that context, I thought quantum computing seemed interesting, and I visited various labs. I visited labs like the Nakamura lab and the Furusawa lab. Since optical types operate at room temperature, I thought it clearly had an advantage, and that's the simple reason why I chose to join the Furusawa lab.
I see. Even if that was your starting point, I imagine you encountered difficulties, or moments when you thought, this is a really tough challenge. Could you share some concrete examples if there are any?
Right. First, just getting familiar with the field. It took me about 2 years before things started to feel intuitive. From a technical standpoint, for example, with the GKP qubits in the phase plane, creating those superposition states is extremely difficult. I've always felt that unless we overcome that challenge, we won't reach practical implementation. In my doctoral work, I proposed a theory that boosts the generation efficiency by about a factor of 1 million. Thanks to that, I feel the path forward is now visible. And every day, I'm eager to see it realized as soon as possible.
Thank you very much. An improvement by a factor of 1 million is truly remarkable. So quantum was a difficult field even for you, Mr. Takase, but also extremely compelling. Mr. Umeki, what led you into this field?
Thank you. As for my starting point, back in university, I was doing research on laser cooling, cooled atoms, which is quite close to the field of quantum optics. A senior in the lab next to mine was even trying to run experiments on quantum teleportation. At the time, I didn't really understand quantum teleportation at all, but perhaps I already had some inclination toward the field. After joining the company, I worked in device research and then became involved in optical communication research. During that period, optical communications were advancing rapidly in capacity. But at some point, you inevitably hit the Shannon limit. While thinking about how we might break through that limit, it became clear that ultimately we would need to use quantum technologies. Yes, I think that was the catalyst for me.
Thank you. Mr. Umeki, in the field of optical communications, particularly in device technology, is one of the world's leading experts, and he has overcome many challenges in advancing high-capacity systems and enabling quantum technologies. Do you have any memorable examples of major hurdles or difficulties that you felt were particularly challenging to overcome?
Right. There are many things I could mention, but I feel that I have been fortunate throughout my research career. I have been blessed with excellent senior colleagues, supervisors, juniors, and team members. That said, the part I struggled with is that everything still took a very long time. As I briefly showed in the slides earlier, I have spent about 20 years working to improve this device. Even in such a supportive environment, it required an enormous amount of time, and many things happened along the way. So perhaps that is the closest way to describe what was difficult, if I can call it that.
Thank you. Progress doesn't come overnight, and after 20 years of work, it feels like we've finally reached this point. Thank you. Before moving to the next question, on November 18th, our company and OptQC jointly announced a partnership agreement aimed at realizing 1 million quantum bits. The announcement was covered by many media outlets and received significant attention, as you can see here. Mr. Takase, you also received a large response, right?
Yes. As you can see, it was a session together with Mr. Shimada. It's not often that an early-stage startup gets the chance to hold a press event alongside the president of a major corporation. Because of that, the response was very strong, and I could really feel how much expectation people have for this.
Thank you. I think everyone here probably wants to ask this as well. Reaching 1 million quantum bits is an extremely challenging goal. So what are the key technical issues we must overcome to achieve 1 million quantum bits, and what needs to happen for it to become possible? I'd like to ask both of you. First, Mr. Takase.
1 million qubits is a very difficult problem. Every approach is aiming for 1 million quantum bits. I believe the optical approach has excellent scalability, so it has an advantage over other approaches, but even so, 1 million is right at the edge of what is difficult. So one point is that we'll need to use every multiplexing method available, including the time-domain multiplexing and frequency multiplexing I explained earlier, and possibly some degree of spatial multiplexing as well. And we'll have to take the shortest possible path using all of them, or we'll likely not be able to achieve it. Let me also mention the device side. With our approach, performance depends heavily on the quantum light source and the OPA as an amplifier. If those do not continue to improve, then even if we line up 1 million quantum bits, we won't be able to entangle all of them. We would end up with many small, fragmented pockets of entanglement, but not an entangled system as a whole, and then multiplexing loses its meaning. So in that sense, I think further advances in the devices are essential.
Thank you. I think what we have just heard is that the devices are the key. Mr. Umeki, with that in mind, what do you think?
First, improving speed is essential. So on the device side, I think it starts with improving the low-noise performance of the amplifier. Also, the strength of entanglement depends on what we discussed earlier, squeezed light. In other words, it is determined by how much squeezing we can achieve. So naturally, we need to improve that performance as well. And if we want to build something like logical bits, this is something I could not cover in the talk, but we need to do things like further superpose Schrödinger cat states. As for how to realize those ideas, Mr. Takase has been thinking about this extensively and has published papers as well. But to make them real, we will likely also need to produce a very large number of quantum light sources with tightly matched characteristics.
Thank you. I hope you'll continue advancing your research and overcome the many barriers ahead. With time in mind, I would like to move on to the final question. Finally, today's computers evolved into personal computers in roughly 30 years after ENIAC was developed. Given the pace of technological progress in recent years, I expect quantum computers may spread even faster than that. Quantum computers, together with AI, are often said to form the core of the fourth industrial revolution. So I would like to ask Mr. Umeki and Mr. Takase what they think society and industry may look like 30 years from now as a result of quantum computing. Mr. Umeki?
The future 30 years from now? That's a difficult question. 2 weeks ago, I had the opportunity to visit the Niels Bohr Institute. It was for an event marking the 100th anniversary of quantum science, held as part of a Denmark-Japan exchange. I had the opportunity to give a talk there. I can't say what that era will look like, but even back then, there was a major breakthrough that went beyond the assumption that classical physics could explain almost everything. Today as well, with generative AI and large language models, many things can appear almost human-like. But if we shift our perspective and begin asking questions such as where human consciousness comes from, there is still a great deal we do not understand. If quantum computers enable breakthroughs in those unresolved areas, then I believe an entirely different world, so to speak, could open up for us.
Thank you. Mr. Takase, what do you think?
To be honest, it's hard for me to imagine. I think that's simply the nature of it. Starting from the world we live in today, we can certainly imagine specific advances such as autonomous driving developing dramatically, or AI becoming extremely convenient. And in quantum computing applications, we often talk about things like drug discovery becoming personalized, among many other possibilities. But to be honest, I still can't picture what everyday life would actually look like as a result. I do think quantum computers will be put into practical use, deployed widely into data centers, and integrated with ION, leading to a world where information processing is done entirely with light. Despite that, I can't really say what kind of daily life that will create. That said, as is often discussed in the context of smart cities, I do have a sense that we may gradually move toward a more human-centered world. Rather than simply being driven around by technology, my broad impression is that the parts that are uniquely human, such as creativity and our underlying values, will become things we can apply more fully throughout our lives, and that society may move in that direction.
Thank you. As we see in concepts such as Society 5.0, we may be moving toward a human-centered society. It would be wonderful if the widespread adoption of quantum computers leads to a society that is richer and full of diversity. Thank you very much. My sincere thanks to Mr. Takase and Mr. Umeki for joining us today, and to everyone here for participating in this session. Through today's discussion, I believe we have been able to share insights into the enabling technologies behind optical quantum computers, the technical challenges ahead, and the future vision that quantum computing may help create. Thank you all very much for joining us today. With that, I would like to conclude this session. Thank you very much.